Welcome back to the Deep Dive. Today we are swapping the CEO playbook for the ant trail.
Interesting analogy.
Yeah, we are diving into systems that are just insanely efficient, profoundly complex, and yet, well, they entirely lack a central leader.
Hmm.
Think about that for a second.
Yeah.
No general, no master architect, just millions of tiny things working perfectly together. How?
That contrast is really the perfect hook, I think, because when we look at human engineering, we so often focus on making, one complex, highly sophisticated robot, something capable of doing everything.
Right. Capability and precision in one unit.
Exactly. Prioritize that. But then you look at nature and the most successful systems out there, things like ant colonies or these vast termite mounds, they achieve incredible robustness, a massive scale.
Through simplicity. Distributed simplicity.
Distributed simplicity, yes, that's the key.
Okay, so our mission today, and we've got a fantastic stack of sources here, is to really unpack this concept of collective intelligence, CI. This is the, well, radical idea that unbelievably complex and resilient behavior emerges just from large groups of simple individuals.
Who are only following local rules.
Only local rules, exactly. So we're tracing how this bio-inspiration, mostly from social insects, ants, termites, how it's revolutionizing how we design, well, everything.
It really is quite broad.
Yeah, decentralized robotics, AI, even, large-scale human organizational structures.
Right.
We really want to know how nature's swarms are rewriting the rules for leadership.
And what's fascinating about the origins of this field, something our sources highlight, is that it often began almost by accident for the pioneers involved.
Really, not a dedicated field from the start.
No, not at all initially. One professor, for instance, apparently avoided biology entirely at first, preferred the clean lines, the predictability of engineering.
I can understand that. Biology's messy.
It is, but that curiosity eventually led them towards computer science concepts, things like distributed systems, parallel computing. And then, when the conceptual challenge of amorphous computing came up, designing systems without rigid centralized control.
Right.
Suddenly studying biology, looking at how fish school or how ants build things, it became the most intellectually compelling way forward.
So it's practical engineering problems driving the look towards biology.
Exactly.
Yeah.
Necessary even to solve these high-level challenges.
It's the ultimate interdisciplinary accident then. You're looking for a way to design a computer that's robustly fault-tolerant.
Right.
Meaning, it won't crash if half its processors fail.
A huge challenge.
And you realize the blueprint isn't in some clean room lab. It's in a dense swarm of synchronizing fireflies.
Precisely. Nature already solved it.
Okay, let's start with that architectural marvel you mentioned, the termite skyscraper.
The fantastic example.
I mean, we're talking about tiny centimeter scale individuals building structures that tower between 2 to 10 meters high.
It's staggering, isn't it? The scale difference.
It really is.
Yeah.
And that's a massive feat of engineering, especially when you realize these are, well, self-repairing mounds with complex internal ventilation systems.
Climate control even.
Climate control. And yet there's no blueprint, no leader coordinating the effort. How? Just how?
Well, the central problem the termites solve is inherent coordination at a massive scale, right? And under constant environmental pressure. These mounds aren't just big, they have incredibly complex internal structures.
Like you said, climate control, fungal gardens, nurseries.
Exactly. And they're constantly self-repairing. The answer, well, like you suggested earlier, it lies entirely in parallelism and decentralization.
Okay, but wait. If there's no central control, how do they ensure the walls meet up perfectly? Or that the ventilation shafts connect? Surely you need some form of, global information exchange, or a master plan to build something that precise.
That's the human bias, isn't it? We always assume precision requires centralized oversight.
Right, we think architects first.
But in the termite world, they use something much, much simpler. Local chemical cues and physical interaction with the partially built structures themselves.
So the building tells them what to do next.
In a way, yes. If a termite senses a change in pheromone concentration or humidity or temperature in its immediate vicinity,
Just right there where it is.
just right there, it performs a simple action deposit, a pellet of mud, move away, maybe start digging. The incredible complexity of the whole mound emerges from millions and millions of these simple, highly localized decisions.
Wow.
There's no central mega termite orchestrating the construction or, worrying about the global integrity of the ventilation shaft. It just happens.
So the structure itself acts as the medium of communication, the wall, the temperature, the pheromones, that tells the termite what to do next.
Precisely. And this is the source of their profound robustness.
Because there's no single point of failure.
Exactly. If some termites die, or if, thinking in a robotic analogy, some individuals need to go offline to recharge, or they just fail entirely, the system doesn't skip a beat. The work is just redistributed across the remaining agents seamlessly.
So decentralization means high redundancy.
Very high. If a system is centrally controlled and that center fails, the whole system collapses, right? That single point of failure.
Yeah, catastrophic failure.
But with termites, they achieve robustness not through like individual strength or intelligence, but through collective, fault-tolerant organization. They're almost designed to tolerate high failure rates among their workers.
That's a really key insight for organizational design, isn't it? Whether we're building software or human teams.
Absolutely.
Robustness isn't about protecting the strongest part. It's about making sure the failure of any single part doesn't bring down the whole show.
Doesn't interrupt the continuous functioning of the whole. That's the goal. Hashtag tag 1.2 emergence from local rules. And this leads us directly to the fundamental mechanism behind all this swarm intelligence emergence.
Right, the magic word.
If there's no leader, how is this complex behavior coordinated? It really boils down to collective autonomy, arising purely from simple local interaction rules.
An individual only needs to worry about its immediate neighbors.
That's it. Aware of and interacting with its immediate neighbors, nothing more.
That concept is still kind of hard to grasp unless you see it in action. What's the classic, maybe the simplest example that really demonstrates this emergence?
I think the most beautiful and widely studied natural example has got to be firefly synchronization.
Ah, yes, the light show.
Exactly. Observers back in the early 1900s noticed these huge groups of fireflies in Southeast Asia flashing on and off together, perfectly in rhythm.
Like a living Christmas tree.
Totally. It looked like this crazy orchestrated light show, a massive grid of living LEDs blinking in unison, and researchers searched desperately for an external beat, a lunar cycle connection, maybe a leader firefly somewhere.
But found nothing.
Found absolutely nothing.
And the mechanism is startlingly simple, right?
Unbelievably simple. Each firefly is basically operating on a fundamental local rule. If my neighbor flashes, I adjust my next flash to try and match their rhythm.
Just nudging its internal clock based on who it sees nearby.
Yeah, trying to move closer to their timing, matching its phase to its immediate surroundings. And this collective phase-locking phenomenon, it occurs all across nature.
Where else?
Well, think about audiences spontaneously clapping in rhythm after a performance.
Oh, that happens. Starts messy, then clicks in.
Exactly. Starts randomly, but quickly converges. Or think about how heart cells synchronize their beats, or even how certain neural activity groups coordinate in the brain. It's the same principle.
So why does synchronization matter? What's the utility? Yeah. Why is it better for everyone to click, click, click together instead of just blinking randomly?
Well, it allows for immensely powerful collective action and information processing. And we need to distinguish this from just simple aggregation, like birds flocking together. Synchronization allows the swarm to act as a single, powerful entity.
Okay, give me an example.
Right. So if you have a network of thousands of sensors trying to sample the environment, say, measuring the temperature gradient across a huge warehouse, it's much more effective if all those sensors click simultaneously. It provides a unified data snapshot of that moment in time.
Like taking a high-speed photograph versus a kind of blurry time lapse.
Exactly that. Or think about pushing a large, heavy object, like an ant colony trying to move a dead beetle.
Yeah, you see them struggling.
Synchronizing the force applied by hundreds of those ants makes them vastly stronger than if they just pushed randomly bumping into each other.
Makes sense.
Or in engineering terms, if you have a group of radio transmitters sending a signal, if they send it at the exact same time, you're superimposing the waveforms. You're essentially shouting together rather than shouting separately.
So you get a much stronger signal, overcomes noise and distance.
Greatly increases the signal strength, yeah. Overcomes signal decay. It's all about coordination for maximum impact, but achieved through incredibly simple local phase matching. Hashtag tag 1.3 amorphous computing and bioinspiration.
So this fascination with decentralized, fault-tolerant systems, it led directly to this conceptual breakthrough you mentioned earlier, amorphous computing.
Yes, that was a really foundational idea in the computer science world. It was pushing back against the very rigid, sequential thinking of traditional circuit design.
What do they mean by amorphous?
Well, the term amorphous computing arose because researchers felt they were thinking too religiously about circuits, you know?
Like everything had to be perfect.
Exactly. Perfectly aligned, clocked, rigidly structured. They decided they needed to treat computing components less like those rigid, perfectly placed elements on a circuit board,
Huh?
and more like particles in physics. Or indeed like fish in a school. Less structure, more fluid interaction.
Okay, what's the practical difference then between amorphous computing and, say, traditional parallel processing? Aren't they both doing things at once?
They are, but traditional parallel processing still usually relies on a global clock and some kind of centralized scheduling.
Right, coordinating everything.
Amorphous computing, however, fundamentally assumes unreliable, maybe even chaotic communication. And crucially, no global time reference.
No master clock.
None. The goal is to design systems where if you literally broke half the computer, meaning half the processing nodes fail, or detach, or just go silent.
Which happens in the real world.
All the time. The remainder would simply self-organize, self-correct, and continue the task. Performance might degrade, sure, but it wouldn't just crash.
Wow, that sounds incredibly challenging technically. If there's no global clock, how do the nodes communicate their state or agree on anything?
That's the absolute core challenge, and that's what drove them straight to bioinspiration.
Because nature already figured it out.
Exactly. They had to design communication rules algorithms where a simple individual node interacting only locally could somehow contribute to achieving a collective goal without ever knowing the global state.
Just reacting to its neighbors.
And this requires designing for inevitable failure and noise right from the start. If a node is trying to communicate, it doesn't know when the message will arrive, or even if the recipient is still there. It just broadcasts locally and trusts that the simple rules of interaction will somehow nudge the collective towards the desired outcome. This necessity really pushed robotics and computation folks into studying creatures like ants, fish, and termites, because they had already mastered this concept of collective autonomy and self-repair over millennia.
And crucially, this whole movement, this ability to actually test these ideas, was driven by the availability of cheap hardware.
Oh, absolutely critical.
It's hard to study swarms if every single unit costs $250,000.
Impossible, basically. Robotics was incredibly hard when computing power was weak and every piece of hardware was bespoke and expensive. But now, with advanced microsensors, cheap processors, a modern cell phone on wheels is essentially a pretty powerful robot.
Yeah.
The cost barrier just plummeted. And this democratization of technology made building and testing large, inexpensive swarms, the very core of amorphous computing theory, finally feasible on a massive scale.
So the theory led to actual hardware. And the kilobots are arguably the most famous platform designed purely for studying collective intelligence. These are tiny, coin-sized robots, right? With really minimalist capabilities.
Correct. The beauty of the kilobots, in many ways, lies in their severe limitations.
Less is more.
In this case, yes. They can only measure distance using a very simple infrared sensor, and they can communicate extremely basic messages locally, like tiny data packets.
Okay. And how do they move?
They have little vibrating motors,
Yeah, no.
which means they sort of jitter around in an unpredictable, error-prone way. Their movement is inherently noisy.
Right, so they don't drive in perfect straight lines.
Not at all. More like a drunken crawl.
Okay, so how on earth do you get thousands of these error-prone, minimally communicative, jittering, coin-sized robots to form a precise shape, like a starfish? That sounds like programming chaos.
It is programming chaos, in a way. But you're programming the rules for the chaos. With these basic qualities, local sensing, local communication, they can be programmed to demonstrate those complex, classic collective behaviors we talked about, like synchronization,
Okay.
but also higher-level tasks like pattern formation and self-assembly.
Our sources describe experiments where, thousands of these robots formed a starfish shape. What really stands out about that example is the autonomy.
Yeah.
Like you said, no single robot had the blueprint.
Exactly. That's the mind-bending part. When forming a complex 2D shape, no individual kilobot knows its final location in the global structure. It has no idea it's part of a starfish.
So how does it know where to go?
They rely entirely on localized rules, often inspired by biological processes like chemical diffusion. Researchers use virtual morphogens.
Morphogens, like an embryonic development.
Exactly like that. Chemical signals that diffuse across the swarm. In the robot's case, this is simulated by broadcasting light signals, maybe using their LEDs, that fade quickly with distance.
So a robot maybe moves towards the light until it gets too crowded, or the light gets too dim, like a chemical reaction defining a boundary.
That's the basic idea. The global shape emerges from those local, imprecise movements, the constant errors, and continuous self-correction among neighbors.
So errors aren't necessarily bad.
Errors are part of the process. If a robot moves too far out of line, the local morphogen signal, it perceives changes, prompting it to maybe move back in. This decentralized error-correcting process allows you to effectively grow a shape.
Grow it like a crystal.
Yeah, using a process much closer to biological development, like how the spots on a leopard or the stripes on a zebra form, rather than traditional top-down blueprint-based assembly. The challenge, however, and it's a big one, is making that difficult leap from 2D patterns on a nice flat tabletop to functional, robust 3D construction in the real world.
Right. Stacking things up adds a whole new dimension of problems. Gravity, stability.
Exactly. When you move to vertical structures, rigidity becomes a critical problem. A small error at the base can lead to collapse. And that's where we turn to new inspiration. Army ants and termites again, the absolute masters of 3D self-assembly.
The army ant bridge is just wild. I've seen videos. They literally link themselves together using their own bodies to create living architecture.
Living bridges, yeah. Across gaps or detours on their foraging trails.
So they can cross faster.
Precisely. But it's far more than just static construction, it's adaptive assembly. This is what blew researchers away. They found the system is inherently tuned to efficiency.
How so?
The bridges only form under high traffic conditions. If the traffic flow is low, the ants prioritize speed and just take the longer route around the detour. They don't waste time and energy building a bridge that isn't needed.
Smart.
And crucially, the width and even the location of the bridge adjust in real time, related directly to the level of congestion.
So more ants crossing means they make the bridge wider.
Exactly. More traffic means a wider bridge to accommodate the flow smoothly. It's incredible.
That is basically congestion adaptive building material made of living bodies. So engineers are now trying to emulate that in robotics,
Yeah.
moving away from rigid lattices and trusses.
That's the push, because rigid structures, like a crystal lattice, propagate defects very easily. A small flaw can spread and cause a major failure. The goal now is to create amorphous and compliant structures. Soft, adaptable robotics.
Okay, compliant meaning flexible.
Yes. The engineering goal is to make soft robots that can climb over each other and link up without needing precise alignment or rigid docking mechanisms, which are complex and failure-prone.
So how are they doing it?
Our sources describe some really cool soft robots that achieve this with a highly stretchable, compliant skin. Almost like a robotic Velcro, but soft and flexible.
Oh, okay.
And their grippers are inspired directly by ant tarsal hooks, the little claws on their feet. They've developed these corkscrew-like devices that can literally screw into the compliant surface anywhere on another robot's body.
Wow, so they don't have to find a specific port or socket? They can just grab on anywhere.
Exactly. They achieve compliant attachment, total flexibility and connection. This is essential for creating those dynamic, temporary structures, similar to what the ants do with their bodies.
And are these connections strong?
Surprisingly strong. Researchers found that one of these simple, flexible grippers can hold the weight of almost 12 other robots.
No kidding.
Yeah, demonstrating how strong this attachment system can be. It allows them to form strong, temporary, load-bearing structures that can be quickly added to or dissolved just as the traffic demands change, mirroring the ants. Hashtag 2.3 implicit coordination underwater. Blue swarm.
Okay, now let's shift the environment entirely underwater. This sounds like the ultimate test for decentralized systems.
It really is, because communication is fundamentally different down there.
How so? Radio doesn't work well.
Right. It's incredibly difficult to get reliable wireless signals to propagate, or to get accurate global localization like GPS. Underwater acoustics are slow and noisy too.
So you can't just beam commands around easily.
No, which makes it the perfect test bed for what's called implicit coordination.
Implicit coordination,
Yeah.
meaning they coordinate without talking.
Essentially, yes. That difficulty forces the system designer to rely only on observation and local interactions, just like natural fish schools and bird flocks do. You simply can't rely on GPS or high-speed wireless data packets. These biological swarms, which we often model using concepts like the Boyd's model.
Boyd's, B-O-I-D-S.
Yeah, like birdoid. It's a classic simulation model. These systems create highly dynamic structures, evade predators, find food, all using purely local rules. No centralized communication network needed at all.
Okay, let's detail those Boyd's rules then, because they seem foundational for flocking and collective dynamics everywhere, right?
Yeah.
And we need to understand how they work when the robots are basically swimming blind.
Great. The Boyd's rules, in their simplest form, boil down to three core principles. First is alignment. You try to match the velocity or heading of your immediate neighbors. Go with the flow.
Okay, makes sense.
Second is repulsion, or spacing. You need to maintain a minimum distance to avoid crashing into your neighbors. Don't get too close.
Right, personal space.
Exactly. And third is cohesion. You try to stay near your neighbors so you don't get separated from the group. Stick together.
Alignment, repulsion, cohesion. Okay.
The challenge underwater is implementing these simple rules based on extremely limited, very error-prone sensing.
How limited are we talking about? What can these underwater robots actually see?
Well, the test bed for this, the Blue Swarm robots, they're small, maybe 13-centimeter units. They have multiple fins, so they can move in 3D space quite agilely.
Okay.
But for sensing, they primarily use simple LEDs. They flash lights at each other to communicate distance and relative heading.
Just blinking lights, that's it.
Pretty much. Now imagine you're one of those robots in a dense school. Your vision system just sees the others as this constellation of moving, blinking dots in a murky crowd.
Yeah, confusing.
And local vision underwater is inherently error-prone. It's highly susceptible to turbulence, currents, and occlusion, other robots getting in the way. So a robot has to somehow translate that messy, error-prone pattern of dots into meaningful behavioral decisions.
Like, which dot is actually my neighbor? Which way is it going? How far away is it really?
Exactly. All from blinking lights in murky water.
That seems like an almost impossible task for a simple algorithm. Are you saying they can actually achieve complex group behaviors like aggregation forming a tight group and then dispersion spreading out with that incredibly low level of input quality?
Yes. That's what the research is showing. And what's fascinating is that the theoretical studies suggest that systems relying purely on this implicit coordination without global knowledge, without direct wireless communication, can achieve a really surprising amount of coordinated behavior.
So they're testing the absolute limits.
They're testing the limits of how far you can push local, fuzzy visual sensing to achieve global goals, which is absolutely critical if you want to use these swarms for real-world applications like, say, ocean monitoring, mapping coral reefs, or coordinating search and rescue in really difficult, murky conditions.
Okay, so we've talked about these elegant designs and the theoretical benefits. But the messy reality, like actually running 1,000 robots for 12 hours straight, revealed some pretty hard lessons about scaling up, didn't it?
Oh, absolutely. Theory is one thing. Practice with 1,000 moving parts is another.
Right. And noise, for example, isn't just random static when you scale up. It becomes predictable noise.
That's a really crucial distinction that came out of those large-scale kilobot experiments. The first big insight was understanding persistent variation, which the researchers actually termed predictable noise.
Predictable noise, like...
Well, in any large group, whether you're observing drivers on a highway or simple little vibrating motors on a tabletop, you will have systematic variation. You will have your slow drivers.
Every system has them.
Exactly. Robots that are consistently and predictably slower than average, maybe due to slight manufacturing imperfections or battery differences or friction. You'll also have persistent, systematic errors in distance measurements that always tend to drift one way or the other for a particular robot. This isn't stochastic noise, random, unpredictable static. It's systematic variation that you absolutely have to factor into your core algorithm somehow.
Got it. And then there are the rare events. This sounds even trickier.
Much trickier.
When you have, say, 20 robots, if one misbehaves, you just notice it and take it out.
Yeah, easy enough.
But when you have 1,000 robots running for 11 or 12 hours straight, a rare, low-probability event like, say, one motor getting momentarily snuck, or a communication packet spiking with bad data, or a robot just erroneously turning 180 degrees and going the wrong way.
Something unlikely for any one robot over a short time.
Right. But with 1,000 of them over half a day.
It's guaranteed to happen.
Yeah.
Several times, probably.
And that single rare error, it can cascade, can't it?
That's the killer. A single slow robot, or a robot that turns around and drives against the flow, can cause traffic jams that ripple outwards and take down the entire system. It can prevent the overall collective goal, like forming that starfish, from ever being achieved.
Ouch.
This led to a really critical insight. It's not enough to just make robust algorithms that tolerate average noise or predictable failure. You need the system itself to develop some kind of internal quality assurance mechanism, what they started calling an immune system.
An immune system.
Yeah.
What does that mean in algorithmic terms? How does a kilobot get diagnosed and, I don't know, rebooted or self-eliminated?
Right, so it means designing secondary algorithms whose primary job is not to execute the main task like forming the starfish, but to actively detect, isolate, and correct misbehavior within the swarm.
Like white blood cells for robots.
That's a great analogy. You simply can't fix every individual algorithm to accommodate every possible arbitrary noise event perfectly. It's intractable. Instead, the collective develops these internal checks.
How do they work?
For example, if a robot fails to move for a certain duration when it's expected to, its immediate neighbors might communicate locally and reach a consensus that this robot is stuck or misbehaving.
So instead of trying to perfectly debug 1,000 individual motors beforehand, you create a collective rule that says if a neighbor is consistently slow or stationary when it shouldn't be, maybe force it out of the line of movement or frag it.
Precisely. The detection algorithms use simple local heuristics. If a robot is behaving way outside the expected norms for a certain period, the surrounding robots might tag it as dysfunctional.
And then what happens? What's the response?
The response is then mandated by the algorithm. The dysfunctional robot might be forced to reboot its local software, essentially giving it a fresh start to clear any transient error.
Okay.
Or in the case of, say, complete mechanical failure where it's just dead weight, the rest of the swarm might actively bypass it or even collectively push it out of the main operational area.
Forcing it to self-eliminate from the active process.
Exactly. To prevent those rare errors from cascading and causing system-wide failure, it's an internal, self-correcting maintenance function that ensures overall system health, even if it means sacrificing a few individual units along the way.
Okay, let's circle back to the army ants for a minute. Researchers looking closely at their amazing adaptive bridges made another remarkable biological discovery about these living structures.
They exhibit hysteresis.
Yes, hysteresis or structural memory.
That is a highly technical concept. We definitely need to unpack that fully. What is hysteresis?
Okay, so hysteresis basically describes a system where its current state depends not just on the current environmental conditions, but also on its history, the path it took to get to that state.
Okay, example.
Right. Imagine an ideal rubber band. Perfectly elastic. You stretch it, you release it, and it snaps right back immediately to its original shape. No memory of being stretched.
Got it. Hysteresis, in contrast, is when the system retains some memory of its history. So if you stretch a different kind of rubber band, one that's maybe a bit old or less elastic, and when you release it, it stays a bit slack. It doesn't fully return to its original tension right away.
Yeah, it remembers being stretched.
That's it. It's exhibiting hysteresis. Its current length depends on whether it just got stretched or just got released.
Okay. And how does that translate to the army ant bridge? How does a bridge remember something?
Well, remember, the bridge is formed by the ants using their own bodies, linking together. Researchers found that the volume of the bridge, basically the number of ants committed to being part of the structure and even its precise physical location, differed considerably depending on whether the bridge was formed during a period of increasing traffic or a period of decreasing traffic.
So if traffic ramped up to 100 ants per minute, the bridge grew to a certain size. But if traffic then dropped back down from 100 ants per minute, the bridge stayed bigger for longer than it would have been if the traffic had only ever reached, say, 50 ants per minute.
Exactly. The structure maintains a memory of the peak traffic it recently experienced, even after the actual traffic has dropped off. It doesn't shrink back down immediately.
That sounds almost like an inefficiency, doesn't it?
Right.
Or maybe even a defect. Why would nature evolve a mechanism that keeps resources ants, in this case, committed longer than strictly necessary based on current conditions?
That's the fascinating question. It seems it's actually an evolved feature, deliberately designed to solve the problem of oscillation.
Oscillation, like things switching back and forth too rapidly.
Precisely. In engineering, we use hysteresis deliberately all the time to dampen oscillations or prevent rapid, unnecessary switching. Think about your home thermostat.
Okay.
If you set it to 72 degrees, if it had no hysteresis, the moment the temperature dipped to 71.9, the heater might kick on. Then, the moment it hits 72.1, maybe the AC kicks on.
Right. It would be constantly clicking on and off for tiny fluctuations. Annoying and inefficient.
Totally. So we build in hysteresis, a buffer zone, maybe a 2-degree window around 72. The heater only comes on at 71, and the AC only at 73, for example. That prevents that rapid, unnecessary switching.
Okay. So the biological hypothesis is that ants evolved hysteresis in their bridge building for the exact same reason,
Yeah.
to dampen oscillations in their self-assembly process.
Precisely that. Think about the environment of an army ant trail. The bridges are constantly under minor perturbation. A gust of wind, subtle ground vibrations, maybe a stick shifts slightly, or they're just temporary lulls in traffic flow.
Right. The world isn't perfectly stable.
Exactly. You don't want the system constantly adding and removing ants, constantly remodeling the bridge structure due to these tiny environmental shifts that might only last for a second or two.
It would waste a huge amount of energy and coordination effort.
A huge amount. The biological mechanism for this memory is believed to involve things like the saturation of pheromone signals on the trail, or maybe the physical interlocking of the ants themselves, which makes dissolving the bridge slower than assembling it initially. Hysteresis provides that crucial structural memory.
So the bridge only remodels when things get tough.
Basically, yes. When traffic flow demands a genuine, sustained change, either up or down, it prevents the colony from wasting energy on constant, pointless micro-adjustments to fleeting conditions. Stability through memory. Hashtag 3.3 fitness function engineering.
Okay, let's shift gears slightly to the AI side of robotics, particularly when you're using things like artificial evolution letting algorithms automatically select for effective behaviors.
A very powerful technique.
Right, but you can't just tell the robot, okay, move your right leg forward, then your left leg. That's programming. With evolution, you have to define the desired outcome
Right.
and let the system figure out the how.
Exactly. And this is the incredibly labor-intensive difficulty of what's called fitness function engineering.
Fitness function. That's the score you give the robot for how well it did.
Precisely. It's perhaps the single most challenging aspect of applying evolutionary algorithms in practice. You're trying to formulate a mathematical function that accurately scores the behavior you actually want, like jumping high, or grasping an object securely, or moving quickly across terrain without explicitly detailing the exact sequence of movements.
And the system optimizes relentlessly to maximize that score you provide.
Utterly relentlessly. If the score is high for a certain behavior, that behavior is rewarded, it survives, it gets propagated into the next generation of algorithms.
Let's use the example from our sources because it makes it really clear. Trying to program, or rather evolve, a quadruped robot, like a robotic dog, to jump.
Okay.
If I'm the programmer and I naively just ask the system to maximize the height of one specific sensor, say sensor Z3, which happens to be on the tip of the robot's head, what happens?
Well, the algorithm, operating purely on cold logic, will find the absolute easiest way to maximize that Z3 score.
Which isn't jumping.
Probably not. Instead of jumping gracefully, it might simply collapse the rest of its body downwards, folding its legs completely, thereby raising that single sensor Z3 as high as possible, while the robot just rests pathetically on its torso.
So it satisfied the letter of the law, maximized Z3's height, but completely violated the spirit of my intent, which was to jump.
Completely. That's a classic example.
Okay, so I, as the engineer, then realized my mistake.
Yeah.
I adjust the fitness function. This time, I ask the system to maximize the duration of time where all 4 of his foot sensors are off the ground. That should ensure it's actually airborne, right?
A reasonable thought. But what loophole might the algorithm find now?
Oh,
It might just lift all its legs slightly, maybe only a centimeter off the ground, and then just rest balanced precariously on its torso or its belly for a very long duration.
so technically, all 4 foot sensors are off the ground for a long time.
Exactly. It fulfills the touch sensor constraint perfectly, but without achieving any actual height or propulsion, still not a jump.
This really highlights the main pitfall then. Perverse instantiation.
That's the term for it, yes. It's when the evolved behavior perfectly satisfies the literal mathematical terms of the fitness function you wrote, but in a completely unwanted, nonsensical, or sometimes even dangerous way. It shows this massive gap between the programmer's intent and the algorithm's literal interpretation of the score.
So the key takeaway here for engineers, or anyone designing these kinds of systems, is you have to anticipate every possible unintended loophole in your goal definition. You almost have to specify the constraints defensively.
Very defensively, like a lawyer writing a contract against an adversarial opponent, which is essentially what the optimization algorithm is.
So to fix the jump problem properly, you'd probably have to combine those scores, wouldn't you? And add more constraints.
Exactly. You have to layer the constraints carefully. You might need to add a term to the function that says, maximize the height of the lowest point of the robot's body while also maximizing the duration of time where all 4-foot sensors are off the ground.
Getting closer.
You're constantly in this iterative battle with the optimization engine, essentially teaching it what a good jump isn't, by penalizing the loopholes until it finally finds the path you actually intended. It often takes dozens and dozens of iterations to refine a fitness function that accurately represents a complex behavioral goal without these perverse outcomes. It's a real art.
Okay, so now let's broaden the scope beyond just physical robots or insects and look at human-based swarm AI. This leverages collective knowledge in a very different way to make superior decisions or predictions.
Right, using people as the agents in the swarm.
Exactly.
Yeah.
But the core mechanism is still inspired by swarm intelligence. It typically uses some kind of mediating structure, often like a neural network, to organize and dynamically weigh the input from large groups of people. It's a system of consensus optimization, not just simple voting.
And the results we saw in the sources are pretty astounding. Take the prediction example. In an experiment predicting outcomes like the Oscars or movie box office success.
Yeah, that one's striking. A swarm of just average movie fans, these are not professional critics or industry experts, they achieved a 76% prediction rate.
Which was far superior, wasn't it?
Miles better than traditional Democratic voting, which in the same experiment scored only 47%, and even significantly better than the professional movie critics, who only scored 64%.
That really demonstrates the power, doesn't it? The collective, when organized correctly through this kind of AI structure, effectively becomes an artificial super expert that can exceed the capacity of even trained individual specialists.
So the secret isn't a simple one-person, one-vote system, is it? It's definitely not just averaging opinions. That's the wisdom of crowds, maybe. But this is different.
Absolutely not just averaging. Simple averaging is the baseline wisdom of crowds. But swarm intelligence, as implemented here, is much more dynamic and nuanced. It works by weighing the input from individuals based on things like their perceived intelligence or expertise, if known, but also their confidence, and dynamically measuring real-time micro-sentiments among the population as they converge on an answer.
How does that work in practice? Are people voting?
It's often more like a shared interface. People participate simultaneously, maybe using sliders or moving a shared virtual puck or cursor towards their preferred answer on a spectrum. This creates a dynamic, real-time negotiation process, a push and pull within the group.
Okay, but how does the system measure that real-time micro-sentiment in a way that's actually useful for weighting the inputs? That sounds tricky.
The AI or neural network structure acts as the mediator. It tracks the small fluctuations, the hesitations, the conviction in the collective movement of that shared cursor or indicator.
So it watches how the group decides.
Exactly. If the collective hesitates slightly before committing to an answer, or if there's a strong pulling force from a subset of the group against the final emerging consensus, this system interprets that dynamic tension as valuable information about the certainty and distribution of opinions.
Yes.
It uses these real-time physical dynamics, the pulling and pushing within the group interface, to dynamically weigh the input. It often gives greater significance to those who express high confidence, but crucially, only when their confidence is immediately supported or reinforced by other nearby agents in the network structure.
So confidence alone isn't enough. You need local agreement, too.
Right. It prevents a single overconfident outlier from dominating if the local consensus is against them. It's very much like a bee colony making those fantastic high-stakes decisions about where to relocate the entire hive.
Yeah, how so?
They converge on the optimal location through this dynamic, complex process of waggle dances and feedback loops, where scouts advocate for sites, but the final choice emerges from collective agreement, not just the loudest scout. It's dynamic consensus building, not simple voting. Hashtag 4.2 coordination in autonomous systems.
Now, looking at coordination in really large-scale autonomous systems, the challenges are just immense. Thinking about self-driving cars, for instance.
A perfect example of where this needs to work reliably.
Currently, any short-term deployment seems to rely on highly localized swarm intelligence, right? Like a car reacting instantly to a pedestrian stepping out or to the braking action of the vehicle immediately in front of it. Very local reactions.
Yes, that's level 2 or 3 autonomy, mostly reactive. But the future vision, that almost utopian iRobot movie scenario,
Yeah.
involves autonomous vehicles operating at incredibly high speeds, maybe bumper to bumper, without the need for traffic lights at intersections.
How would that even work?
Because they're all assumed to be fully aware of the system and each other, communicating constantly. It's a complete shift in thinking about traffic flow. It moves the complexity away from centralized global governance, like a city managing traffic lights and speed limits, to a completely distributed network of local interactions, potentially mimicking the efficiency and seamless flow you see in a massive ant trail, but at, 70 miles per hour.
That sounds efficient, but also fragile maybe.
Yeah.
And it raises the challenge of specialization, doesn't it? If every single car is programmed identically, they might execute their local rules perfectly. But would that be the optimal way for the whole system to behave? Should we maybe introduce division of labor like we see in insect swarms?
That's a really key question and an area of intense research right now. When researchers studied evolved hunter swarms in simulation like simulated lions trying to cooperatively catch simulated prey,
Okay.
they found that the best overall group performance was achieved not with homogeneous clones where every lion used the exact same hunting strategy.
Oh, works better.
Systems that incorporated specialized roles within the hunting pack. They achieved this in the simulation through something they termed restricted breeding.
Restricted breeding. What did that entail in the simulation?
It basically meant that the individual behavioral algorithms of the, say, 4 simulated lions were allowed to evolve somewhat independently, rather than being forced to be identical copies. This allowed them to develop specialized strategies based on their role or position.
Ah, okay. So they weren't perfect clones.
Exactly. When all 4 lions had the exact same strategy clones, they coordinated, sure, but not optimally. They might all try to flank the prey in the exact same way, leaving another escape route open.
Right.
The overall winning strategies emerged when they used this restricted breeding approach, often combined with position-based sensing. This allowed for the natural evolution of specialized roles within the collective.
So one lion might evolve to be the driver or the front attacker, pushing the prey.
Yeah, while another specializes as the flanker or the interceptor, cutting off escape routes. They work together, but with different jobs.
That suggests that division of labor, or heterogeneity, is actually a much more advanced and effective form of coordination, doesn't it?
It strongly suggests that, yes, even in highly decentralized systems, specialization seems to drive superior group outcomes compared to simple uniformity or having everyone be a generalist. It's a more sophisticated level of swarm intelligence. Hashtag 4.3 swarm dynamics in human society and social norms.
Okay, so this research extends beyond AI and robots, directly into understanding human social systems as well.
It really does. It offers a new lens.
We often assume that large-scale collective behavior in humans requires central institutions or mandates like the government has to change the driving rules or introduce new educational standard for it to happen.
Right, top-down change.
But these swarm principles suggest that social change, the emergence of norms, can actually happen organically, maybe even faster, based purely on the network structure of our interactions.
That's the core implication here, and I agree. It's profound for understanding how human organizations and societies actually work or how they change.
There was that name game experiment mentioned in the sources.
Yes, a fascinating study. In this test, people were put into a structured communication network, online usually, and their task was simply to agree on a name for a face they were shown.
How do they coordinate?
Individuals could only coordinate locally. They could only see or interact with their immediate neighbors in the predefined network structure. They'd see the name their neighbor currently preferred, and they could update their own preference based on that local information. Critically, they had no sense of the larger population size or what the universal consensus might be shaping up to be.
Just local gossip, essentially. And what were the variables the researchers changed in the experiment? How did they structure the network differently?
They manipulated the network structure itself. That was the key variable. They tested things like dense connectivity, where everyone knows almost everyone else, like a small village, versus sparse connectivity, where everyone only knows a few people, maybe like a long chain.
Okay. And what did they find? Did the name always converge?
They found that the global outcome, which name ultimately won popularity and became the agreed-upon social norm for that group, was controlled almost entirely by the structure of the network and how people interacted locally.
Not by, say, which name was inherently better? Or who started with it?
Not primarily, no. It was the network topology that mattered most.
So what happened in the sparse networks?
In sparse networks where information flowed slowly, consensus took a very, very long time to form, if it formed at all. Different pockets of the network might settle on different names and never reconcile.
And in the dense networks?
In dense networks, consensus was usually reached very quickly because information spread rapidly. However, these dense networks were also highly susceptible to random initial conditions. Whichever name got a slight early advantage could quickly sweep the whole network, even if it wasn't necessarily the best name.
So the critical finding was that the network structure itself dictates both the rate of convergence and the final outcome.
Exactly. The experiment really demonstrated that social change and the emergence of widespread norms can potentially take place over large populations without any central institutions pushing it. It can depend purely on the patterns of connection between individuals.
Wow, that implies that a small group, maybe with a focused agenda, if they were positioned correctly within a social network structure, perhaps acting as highly connected hubs or as bridges between otherwise separate communities, they could potentially influence or even govern the outcome for the entire collective just by changing the local rules of interaction or how information propagates through them.
That's the provocative implication, yes. The lesson seems to be that if you want to promote a new idea or a product or a social norm, simply broadcasting the information widely might not be the most effective way.
You need to think about the network.
You have to understand and maybe even try to structure the interactions, the local feedback loops, the connections, to favor the propagation of that specific idea. The structure of our social interactions, whether online or offline, might be what fundamentally determines which norms become possible and which ones die out. Hashtag 4.4, the ethical and organizational future.
Okay, as we project the swarm technology forward, whether it's robots or AI influencing human groups, several big organizational and, frankly, ethical questions arise.
Absolutely. We have to consider the implications.
The first one seems to be this inevitable shift we're already seeing in robotics, moving away from purely homogeneous swarms, where every robot is an identical clone towards heterogeneous swarms.
Yes, that mirrors nature much more closely. We're moving beyond the maybe naive early goal of making every single robot an identical multi-purpose generalist.
Like you said with the ants, right? They aren't all the same.
Exactly. In nature, ants are never doing just one task simultaneously. Some are out foraging, some are defending the nest entrance, some are inside nursing the larva. They often have specialized hardware, different body shapes, different jaw sizes, different chemistries, and they definitely have specialized behavioral repertoires.
So future robotic systems need to mirror that.
It seems highly likely that the most effective systems will. Incorporating robots with specialized hardware designed for specific tasks, some for heavy lifting, some for delicate sensing, some for communication relay, ensures a much more advanced, adaptive, and efficient division of labor within the swarm.
And this idea of simple specialized robots leads directly to a potential economic shift, doesn't it? The democratization of this technology.
It really could. If robots are simple and specialized, they can potentially be made incredibly cheap and mass manufactured.
Which could be a huge disruptor.
Potentially the biggest disruptor. We could move away from relying solely on extremely expensive, centralized, all-purpose machinery for large tasks, towards deploying vast numbers of low-cost, perhaps even single-use or biodegradable specialized robots.
Single-use robots? Like what?
Well, think about the potential for environmental cleanup or restoration. Imagine deploying 1 million tiny robot bubbles, maybe chemically produced, programmed simply to plant a single seed in the right soil conditions, or to find and encapsulate a specific type of microplastic particle,
Wow.
each with its own tiny local energy source. You deploy them en masse, rather than using one large, expensive, centralized ship or tractor covering the same area much more slowly and clumsily.
That dramatically changes the economics of deployment, doesn't it? It could make massive-scale environmental or agricultural tasks feasible for smaller organizations or developing nations.
Exactly. It lowers the barrier to entry for large-scale action.
Okay, but finally, we absolutely must acknowledge the ethical challenge here. These resilient, relentless, self-organizing systems. If they were weaponized, that's a frightening prospect.
Deeply frightening. It's something the research community is acutely aware of and discusses constantly.
So how do researchers ensure they are focusing on the beneficial civil applications without completely ignoring or enabling the potential for abuse?
Well, researchers consistently emphasize that the fundamental design constraints placed on these systems from the very beginning must focus on trustworthiness, transparency, and controllability. The explicit goal is almost always stated as developing civil applications: search and rescue, firefighting, logistics, environmental monitoring, collaborative manufacturing, healthcare delivery.
But how do you build that in technically? How do you make a swarm trustworthy?
Technically, it means building in specific constraints and safeguards right into the core algorithms and communication protocols. For instance, designing the communication protocols to be open and auditable so you can understand how the swarm is thinking. Ensuring that control mechanisms are designed not just for high performance and autonomy, but also explicitly for human monitoring and intervention.
So even if the system operates autonomously most of the time,
Human oversight nodes, or designated shepherd robots, must be able to inject commands, override collective decisions if they seem to be going wrong, or trigger an immediate halt operation across the entire swarm. There needs to be a kill switch, essentially.
so the inherent resilience of the system has to be balanced by a capacity for robust human control.
Exactly. Ensuring that the technology is designed for monitoring, for ethical deployment, and for fail-safes from the ground up. It's an ongoing challenge, but it has to be central to the research agenda. Hashtag tag outro.
Wow. Okay, this deep dive into collective intelligence, it really shows that we have so much more to learn from the ant trail or the termite mound than we ever realized. Let's quickly try and summarize our key insights for you, the listener.
Sounds good. I think first, the big one is robustness is almost synonymous with decentralization. That ability to tolerate high failure rates, it comes from building complexity layer by layer, locally, without relying on a single critical hub.
Right, no single point of failure.
Second, bio-inspiration provides proven local rules. We don't always have to reinvent the wheel. Things like the Boyd's model for flocking or the pheromone-following rules for termite construction. These give us blueprints for complex coordination using only observation and local interaction, even with really noisy, low-quality sensing.
Okay. And third, that fascinating idea about memory.
Yes, third, adaptive systems often have memory and damping mechanisms. The discovery of hysteresis in army ant bridges shows us that structural memory isn't a bug. It's often an evolved feature, essential for stability. It prevents systems from wasting constant, unnecessary energy reacting to tiny, fleeting environmental changes.
Right, it stops the oscillation. And finally,
Swarm principles applied directly to human collectives and predictive AI. Organizing a collective, whether it's specialized robots hunting together or a group of movie enthusiasts predicting the Oscars correctly, leverages distributed knowledge and allows for specialization to achieve results far superior to traditional centralized systems or just relying on individual experts.
but it requires careful design, factoring in things like real-time sentiment, confidence, and maybe even developing specialized roles within the human swarm.
Precisely. It's not just throwing people together.
So what does this all mean for us, as we design our future organizations or our AI systems or maybe even our educational structures?
Well, the ant colony, the termite mound, the firefly swarm, they all teach us that the highest form of collective intelligence doesn't necessarily require a single, perfect leader or flawless global planning dictated from the top down.
Instead, maybe it requires a really robust, proactive immune system, something constantly working at the local level to detect and eliminate those inevitable, local, rare errors and systematic noise before they cascade.
That seems to be a key lesson. It shifts the burden of leadership, perhaps, from flawless centralized strategy to enabling resilient local self-correction.
Which raises a final provocative thought for you to consider. When we design our future systems, our companies, our software, our societies, should we maybe stop spending quite so many resources trying to achieve perfect global control and centralized oversight?
Which is often impossible anyway.
Right. And instead, should we focus much more intently on designing sophisticated, effective, self-correcting mechanisms right down at the local level?
Maybe the best way to lead a massive organization isn't to issue perfect directives from headquarters, but to ensure that the people or the agents on the front lines have the simple, clear rules, the local information, and crucially, the authority to self-correct the inevitable mistakes quickly and locally without needing to escalate everything.
It suggests the true power isn't always in the grand blueprint. Maybe it's more in the constant, quiet, adaptive resilience of the swarm itself.
Something to think about.